All right, hi folks. I made a few changes to this lecture, and I thought since I have to practice it because I'm gonna be teaching it too, I'd kind of go through it with you. So the goal of this activity was a little different than some of the other labs. In some of the other labs, we've practiced or delved further into applications. In this lab, we're gonna look at talking about transformations from the point of view of why do we see what we see. So if you can go back in your notes and ask yourself, what does the effect of each of these parameters, A, B, and C, have on the graph? I'll give the students about 3 or 4 minutes to get settled and to get out their notes. What they'll see in their notes is that the A causes a reflection across the x-axis and vertical dilations. The B causes a horizontal shift in the direction of B. If B is positive, it goes to the right. If B is negative, it goes to the left. They got to remember it's the opposite sign. If it's plus, I think I even just said it wrong. The point to make here is we want to stop memorizing what it is that happens and try to see if we can ask ourselves, why is it happening? And finally, C is a vertical shift. So the questions that we want to get into are, these are the observations, or these are the results. The question is, why does this happen? Why does A cause a reflection over the x-axis? All right, so that's what I want to say here. So let's look at what's going on when we change, oh my goodness, that should say the parameter C. I'll make myself a note to change that to make it parameter C. Parameter C in slide 4. So what's really going on when I change this value C here? So what we have is f of x is equal to x squared, that's the red, and g of x is f of x plus c, where c is either increased or decreased. And what it looks like is you're taking the whole graph and just moving it up. But if that were the case, then how come it looks like there's more area here than there is up here? It looks more narrow there. So let's look at it from a point-wise perspective. Is that what's really happening? So to do that, all you need to do is to click on this little point, this little folder here, and that reveals the contents of what's in this folder here. What we see is that as we move this point around, it's actually called point P, what do you notice? It actually is the case that for each point, the difference between the transform point and the original point is 3.5. So even though it looks as though it's sort of closer and getting together, I mean, it almost looks like they're going to touch it a little bit. It is the case that for every point, 12.5 minus 9, it might be nice to make this a number like 4, right? 13 minus 9 is 4. 16.25 minus 12.25. The difference is always going to be 4. So what can we say about f of x minus g of x? The answer is that no matter what x is, the answer is always going to be 4. So let's check that out. If I just type it in, f of x minus g of x, it should have given me, well, we can do it this way. What is f of p, because p is that number, minus g of p, right? And you can see it says -4. Oh, that should have been the other way around, I guess. It should be g of p minus f of p. So that means that, you see, it's always 4. No matter how I move this point P around, this number 4 always stays constant. And hopefully that's helpful in terms of a point-wise perspective, but it's also going to be helpful because we're going to use that trick when we look at the A as well. So the idea is that looks can be deceiving, but for any given x, the difference between these two functions is the same. But it's always going to be 4. So is that going to be what happens if we change the function? Suppose we change it to the square root of x. I'm sorry, the absolute value of x. So you can just change that by hitting the shift and the absolute value sign, x, and delete that, and then you have the other absolute value. All right, Now it's a little bit more clear, I think, in the case of absolute value, because linear functions obviously are going to have always the same. So that works out the same. But what if we make it the sine of x? All right, we have to make it the sine of x. Don't make it a capital X. There we go. Again, you'll see that as you move the number around, the point p, sorry, even though it's hard to tell the difference, notice f of p minus g of p still remains 4. If I move this to 3 or 1, you can see that the difference is always 1. So it's important to point out that function notation there. All right, let's move on to the next one here. So when I change the value of c, the graph will change by. So give them a little bit of time to think about that. I'll give you a little bit of time to think about what you would expect them to write.